Hello, welcome to the June edition of Theme Park. This month, we are discussing about facade engineering. And in this teaser, we have with us John, Yvonne, and Andrew. Hello, team. Thank you for joining us. Would you like to introduce yourselves?
Hi, my name is John Kimberlain. I'm a senior scientist for technical services and development for Dow Performance Silicones.
My name is Yvonne Diaz, and I'm a senior research specialist for technical service and development for Dow Performance Silicones.
My name is Andrew Dunlap. I'm the building technology studio leader at SmithGroup.
The topic of your paper is structural silicone glazing at 50 years. What is the background history of the building leading up to the use of silicone in structural glazing?
The building was originally designed with heavy masonry walls and reinforced concrete. And 60 years later, the design team wanted to drastically renovate the building by introducing a total glass facade. Around the same time, silicones were being used in facade-type applications, and the design firm chose to go with a completely innovative idea to use silicone to adhere the glass to the face of the building.
The background is that it was an older building that was going to be remediated after a architectural and engineering firm bought it. It's located in Detroit near the river, and originally it was brick, and in that time, era 1971-72, silicone sealants were being used in facade type of applications, and so the design firm wanted to do something unique and innovative, and they decided to see if they could glue glass to the face of a building.
The history of this building is actually quite unique. It's currently known as the 455 West 4th Street building. It used to be known as the Cass building. It's a 5-story reinforced concrete frame building with mass masonry and punched windows infilled in between the concrete. So it was originally designed in 1910 by Smith Henchman & Grillis, currently known as SmithGroup, as an investment property that had many uses throughout its life. It was an office, it was light industry, light manufacturing. But in 1970, SmithGroup was looking for a new home for its headquarters and found one of our old designs, and it was perfect to house our current staff at the time. So we purchased the building in 1970. We wanted to show off the modernization of the building itself and the facade, and show off how our technical competence and innovation and use the facade to do that. So we've had a long history working with Dow and ASTM, working through structural sealant technologies and helping write with standards, and use that history to want to take advantage of this new technology and apply it to our facade. So this was going to be an overclad. So we had to strip off the mass masonry and the punched windows and apply a totally new custom curtain wall system to it. So we wanted to modernize the building, which included modernizing the facade of the building. Given our long history with Dow and ASTM and our familiarity with structural sealants, we wanted to look at this emerging technology of using it to totally hold the glass onto the frame, all 4 sides, 4-sided structurally glazed curtain wall. That being said though, because it was a little bit newer method of applying this technology, we did add these spider fittings to the wall in the event there happened to be an issue. But having the spider fittings on the wall, we knew that this wall could handle it without it. So we took it to the laboratory, did wind load testing on the complete wall assembly to industry standard tests, and we were actually developing those industry standard tests as we were doing it. Passed all those tests with no issues, no broken glass, no problems whatsoever. And keep in mind, the spider fittings were not on when we did that test. But just to see what this wall could do, we then applied the spider fittings to the wall and tested it to failure. We tested it till the glass broke. We got to nearly 2 times the design requirement with the spider fittings on and passed with flying colors prior to that.
And what has evolved in structural glazing application since it was first used as the sole means of attachment?
In the 50 years since silicone was first used as the sole attachment point of glass to a building, there's been countless new advancements to make silicone stronger, more efficient, and safer for the environment. We can now use silicone to help glass withstand impacts from hurricane debris or a bomb blast. And the chemistry behind the silicones is also constantly evolving to keep the same performance, but to be safer for the environment and health of the users.
That's a pretty long answer because it's been 50 years since the original use in a 4-sided structural application. Originally, that sealant was an acetoxy chemistry, and so acetoxy just means it gives off acetic acid as it cures, smells like vinegar, kind of the stuff you buy in a hardware store. Since then, a lot of different chemistries have evolved and are better suited for this. The acetoxy was a bit rigid or stiff in its connection. Now there are neutral cure sealants, different filler packages that are a little bit more flexible. The way that buildings are constructed now have evolved, and in the use of two-part sealants that cure rapidly allow people to fabricate buildings in a factory setting and then ship the units to be constructed or put on the side of the building. A lot of innovation in the use of sealants in protective glazing type applications. So things like bomb blast or hurricane, silicone sealants are well suited for that type of application. It provides a flexible anchor, helps retain the glass in the event it's struck by debris from a hurricane or in a man-made disaster like bomb blast. So I really wanted to talk about from an innovation standpoint, is that silicone sealants were originally used in architectural type applications in 1958. It was on a building up in Wisconsin where they were sealing glass tubes to prevent moisture intrusion, and it historically had been leaky. It built in 1948, had leaky problems until 1958, and the silicone sealant was used to seal between those tubes and stop the leaks. And it was removed in 2013, not because the sealant was failing, but because they just wanted to update the look of it, collected dirt, things like that. So the reason why silicones were used in this type of application is because of its inherent durability. And so you see a progression in the use of weather seal applications like I just described into more structural applications, total vision systems where they're trying to attach two plates of glass with a fin in the back to give it a more open look. That was in the mid-60s. And then as we progressed into the 70s, 1971, 1972, they used the material to attach the glass to the facade. So if you look at a picture of the building, you'll find that there are these spider fittings all at the corners of the facade. And one of the unique things about that is they really don't have any types of mechanical retention. They're not there to hold pieces of glass in. The story I've heard is that when people walked by and saw this monolithic sheet of glass walking on the side of the building, they had such a visceral reaction to it, didn't know what was holding it in place. They decided to put those spider fittings on there to make it look like something was holding it in. And if you go up to the windows, and we had a chance to visit it last year, you could actually take and spin the spider fittings freely. So we did confirm that there's not a lot of mechanical retention there.
So what has evolved in the structural applications of the various types of sealants over time? I think the two biggest things that I have from a sealant app installation standpoint is the sealant technologies themselves. So at the time we used the same sealant for the structural sealant and for the weather sealant, all one basic application. Now with more modern sealants, you may have a desire to have one type of sealant be used, the structural sealant, and maybe a different type of sealant, something maybe with more flexibility or more movement capability for the weather seal. So we have opportunities to kind of mix and match those sealants when we need to. The other big one, recent technology, is if we ever had to replace this glass. You know, the older technologies took time to cure out, especially with a field application of that sealant. We now have newer sealant technologies that can cure much faster, so you don't have to have that time lag between when you install it and when you actually have to go finish the work. So those are probably two of the big ones from an architect's standpoint that I think have been a lot of benefit to the industry. But then the other big one is the development of the rigorous testing and laboratory procedures of all of these sealants. This project was, kind of the beginnings of how do you develop what that lab protocol should be. How many types of sealant tests should you do? What are the sealant tests? What are the laboratory tests that need to be done? And that continues to evolve. Our technical staff, along with ASTM and Dow, were involved in developing a standard, ASTM C1401, which again has continuous improvement of what do you need to do this correctly, to install these things correctly on any given building. And most recently, I guess, in the big picture scheme of things, is I mentioned we did wind load testing on the glass. Now we do seismic testing. So we move this thing side to side and up and down and all over the place. So it's that continuous improvement of the types of testing to make sure we're still getting a very rigorous product that's going to withstand the test of time.
And my last question, what are unique aspects about the design and the conditions that the building has experienced since it was installed?
In a typical year, the building can experience a flux of temperature changes from a freezing 17 degrees Fahrenheit to over 80 degrees Fahrenheit, with wind speeds up to 40 kilometers per hour. When we studied the historical weather patterns in the area, we also found that there had been several tornadoes in the vicinity of the building, which suggests that the building might have seen wind loads that were much higher than it was originally designed for. Against all the elements, the building and the silicone that holds up its facade has stood the test of time and has really weathered the storms over these last 50 years.
I'm going to talk about the conditions. And so a building in the Midwest typically doesn't see a lot of large wind loads. However, when we reviewed the historical weather patterns, we did find that there had been tornadoes in the area, indicating that there's a potential for this building to have seen some decent sized wind loads compared to what it was designed to. Its location near the lake, one of the Great Lakes, it's going to see lots of rain. It's going to see lots of snow. It's going to see lots of temperature changes, freezing weather up to brutally hot, like where I live here in Kentucky. So the building's seen a lot of elements. It's right next to a very busy thoroughfare in downtown Detroit, so it also sees environmental pollution and things like that. We talked about lots of temperature, lots of rain, maybe some excessive wind events, and after 50 years it's still performing. So again, talking about inherent durability of silicone materials in this type of application, I get asked often, how long is a silicone sealant going to last? And I really don't know. In a well-designed unit, it should last a significant amount. The first one here has lasted at least 50 years, and we've improved technology. We've improved how we design and fabricate things, so it should be a very durable option in this type of application.
So what are the unique aspects about the design and the condition of the building since it's been installed? All right, there's a few big ones here. The first and foremost is weather conditions. In Detroit, we go through some, believe it or not, pretty extreme weather conditions. It's really cold here in the winter, below 0 degrees Fahrenheit easily, and in the summer it can easily get to beyond 100 degrees Fahrenheit too. So there's big temperature swings that we have to go through. But even more importantly on that is we go through significant temperature swings in any given 24 hours. So it's not unheard of that we'll go through a 50-degree temperature swing. That puts the systems through a lot of stress. It's one thing to go through gradual temperature changes, but the quick temperature changes is really what's having to go through here. And then related to weather as well as wind. We have significant wind events here that you'd be surprised of. Just last week we had 50-mile-an-hour wind gust hitting our buildings down here in Detroit, right downtown. And historically, it's not unheard of to go between 50 and 80 miles an hour wind gust hitting our buildings. So that's why we take it to those laboratory tests and really stress them out to make sure they're going to be able to withstand that. So that building's gone through its fair share in the last 50 years of a lot of different rain, a lot of different wind, a lot of different storms, and it's still holding up still today. A couple other things that it's gone through, occupancy changes or lack of occupancy. Detroit has gone through a lot of different changes over the years. Sometimes that building has not been occupied, and we all know when buildings are unoccupied, that's when things happen. The weather can get in, people don't notice it, and it can start to cause damage to the building facades and the interiors of the building. So again, it's gone through those periods of time, and it's certainly surviving it. A couple little testaments of the building. There's another story out there. This building has lots of little stories. That there was a wing nut or a lug nut or something that flew off a car and broke a piece of glass. Regardless of what broke the piece of glass, the glass broke. It didn't stretch to all 4 sides of the mullions, so it got 3 but not all 4. And what's interesting is that because of the structural sealant, the glass stayed in the opening for 3 days before they had a chance to be able to replace it. So again, an attribute of the structural glazing that allows for that to stay in place and not fall out after it was broken. And then lastly, related directly to that and also back to those spider fittings that we were talking about, they're very useful for structural reglazing. Even though we have advanced technologies of faster curing sealants, those spider fittings can actually be used as temporary restraints while the sealant's curing. So Somebody who has to reinstall a piece of glass on that building doesn't have to have temporary clips or anything like that. They can use the spider fittings over, use them to retain the glass while the sealant is curing up.
Thank you. Thank you so much, Tim, for this teaser of your paper. And see you in the huddle.